Boom! Yes folks, you me again. How are you going? In this series of videos, we're going to talk about indices. In a previous video, I spoke about the difference between multiplication and exponentiation, what I referred to as exponentiation. That is not a common word in mathematical lingo, but that's what it is, right? We discussed multiplication as repeated addition, and we discussed exponentiation as repeated multiplication. So in this discussion and in the series of videos following this one, we'll be on the side of exponentiation, the whole question of repeated multiplication. What do we do when we have to deal with exponents, when we have to deal with powers, when we have to deal with indices? What do we do when we have to deal with numbers that are raised to a particular power? All right, and then of course the reverse of that is roots, but we will get into that a little later. So I want to introduce some laws, some rules, and I want to state and emphasize at the beginning how important it is to be absolutely and totally familiar with all the rules that we're going to discuss here in this series of videos. Just as they have rules in all the other topics in maths, this topic, indices, these rules that are going to introduce are fundamental. These rules are rules that they're going to use at all levels once you're dealing with powers. So don't give in to the bad habit of skipping through the video and running through and hurrying. Take your time. Listen carefully to everything that I'm going to say here. I'm going to illustrate using examples so that you can catch it. And then, after you catch it, the most important part is to practice. And that is where you now will have to go and find questions and whatnot to practice. The practice is what will drive the point home. Right, so enough talking, let me get the show on the road. So we have these rules of indices, these laws of indices. And the first one, well, my first one, right, how I'm going to do it here will be a little different to what you will see in most textbooks. But we're trying to do it as comprehensively as possible. The first rule is that anything, let me say if anything, raised to the power of 0 is equal to 1. Now, we're starting off with this special case because what a to the 0 means, there are separate discussions for that. Right? How a to the 0 relates to other powers is an easier thing to understand, but we will get to that a little later in other videos perhaps. But this, you have to remember, anything raised to the power of 0 is equal to 1. And in the course of your various calculations, very often you'll end up with a situation where you have, let me say, 5 to the power 0, or 3 to the power 0, or 7 to the power 0. Or you might have a half to the power 0. You might have 0.3 to the power 0. You might have negative quantities as well, raised to the power 0. Yeah? You might have minus 2 in brackets to the power 0. You might have minus 4 in brackets raised to the power 0, etc., etc., etc. Anything to the power 0, it doesn't matter what anything is. 5 to the power 0 is 1. 3 to the power 0 is the same 1. 7 to the power 0 is 1. Minus 2 to the power 0, 1. Half to the power 0 is 1. Minus 4 to the power 0 is 1. 0.3 to the power 0, 0.3 to the power of 0 is 1. End of discussion. That is what it is. So even if you don't fully understand the detailed mechanics of 5 to the power of 0, just understand that 5 to the power of 0 is 1. Even if you find it difficult to visualize 5 to the power of 0. We know what 5 squared is, 5 squared is 5, multiply by 5. We know what 5 cubed is. 5 cubed is 5 by 5 by 5. You could actually physically see the 5 3 times. So you could relate the 3 5s that you're seeing to the power of 3. So that's easy to visualize. If we have, let me say we have 5 cubed is equal to 5 by 5 by 5. Alright? You could relate these 3 5s to this 3 here. You could connect, you could visualize. What happens when we have 5 to the power 0? How do we visualize that? How do we write that on the board? That's a different question. We will address that another time. But for the time being, just understand that anything raised to the power of 0, the answer is 1. Stick with that. We're ready to go through the rest now. Alright, so in this video, we're going to do a little continuation of the first rule, rule 1, where we said that anything to the power of 0 is 1. And we're going to do that by taking a special interest in the number 1, and we're going to look at the other side of the coin now. It's almost a different rule in itself, but in as much as the number 1 is the centerpiece of the first rule, we're going to extend the discussion focusing on the number 1 but in a slightly different way. And we do that by saying that 1 raised to any power is still equal to the number 1. Alright? That is probably the simplest rule of indices that there is. And that is probably the one thing that everybody remembers about indices, almost without fail. That 1 raised to any power is equal to 1. It doesn't matter what the power is. It doesn't matter what the mathematical nature of the power is. The answer will still be 1. Yeah, the answer is 1. So 1 to the power 3 is 1. 1 to the power 4 is 1. 1 to the power 0.5 is equal to 1. 1 to the power of minus 0.362 is also equal to 1, etc., etc., etc. Nothing else really to be said about that. 1 raised to any power is equal to 1. So in the same way that we know now that anything raised to the power of 0 is 1, then by the same token we know now that 1 raised to any power is still equal to 1. Yeah, that's it. Nothing else to say about this here. Alright, so stay tuned. Stay tuned. We have plenty more coming up in this series. The second rule I want to introduce is when we have to multiply two numbers where both numbers are raised to a particular power. The catch, however, is that both numbers are the same. The powers don't have to be the same. So when we doing our exponentiation, if we say a to the power of m multiply by a to the power of n, there's a particular rule for that. And the rule for that is that a to the power of m by a to the power of n is a to the power of m plus n. That is the rule again. I'm not going to go too deep into the demonstration in this series of videos. Basically, I'm just going to give you the law, illustrate the working of the law, and then leave it up to you, wherever you go, to get deeper into the practice, into the explanation. So For example, if we have 5 to the power of 3 multiplied by 5 to the power of 4, that is equal to 5 to the power of 3 plus 4, which is equal to 5 to the power of 7. If we have 12 to the power of 6 multiplied by 12 to the power of 2, that is equal to 12 to the power of 6 plus 2, which is 12 to the power of 8. Now it works with negative indices too. So if I have 12 to the power of minus 3 multiplied by 12 to the power of 4, that will be 12 to the power of minus 3 plus 4. Minus 3 plus 4 is 12 to the power of 1. If I have, it works with fractional indices as well. If I have 7 to the power of 3 over 2 multiplied by 7 to the power of a half, that is equal to 7 to the power of 3 over 2 plus a half. 3 over 2 plus a half is 4 over 2 equals 7 to the power of 4 over 2. I have a separate video on adding fractions too, right? 7 to the power of 4 over 2, which is equal to 7 squared, etc., etc., etc. What about when we have all negative indices? We could do that too. So let me switch, right? So I have all the examples here. We're going again. If I have, let me say, 9 to the power of minus a half multiplied by 9 to the power of minus 3, then the answer is 9 to the power of minus a half plus minus 3. Right? Notice we're using the brackets and so forth. Nice? That is equal to 9 to the power of minus a half minus 3, which is equal to 9 to the power of minus 3 and a half, etc., etc., etc. So let me do a simple example with the negative numbers. I feel that half would spook some of you out. So let me make life a little easy now, right? So simple example. If I have 2 to the power of minus 3 multiplied by 2 to the power of minus 7, then that would be 2 to the power of minus 3 plus minus 7, which is equal to 2 to the power of minus 3 minus 7, which is equal to 2 to the power of minus 10. Yeah. And that's it, you know. Now, I want to make a very important distinction between what happens when we multiplying and what happens when we exponentiating. Now, before I do that, notice that the only way this rule applies is if we have the same base. All the examples that I would have used up to this point involve the same base. The 12 and the 5, in this case the 2, in this case the 9. The powers could be different once the base is the same. So in other words, we cannot then say that we cannot say that 5 to the power of 3 multiplied by 10 to the power of 2 is equal to what? I know that there are people who would do this. 15 to the power of 5. People will do that. And that is not, how to put it, that is a mistake that you could understand. I could understand why somebody would put that. Right? Because you tell yourself, well, if you're adding the powers, then you might want to add the bases too. And it makes logical sense. But just like a lot of things in life, even when it makes logical sense, it may not necessarily be the correct thing or the truth, right? So anytime the bases are different, do not even think of using that rule, this rule here in black. And unlike multiplication, there is no case where you could factorize. You can factorize here. Right? So you can't say, well, all right, because you have 5 here and you have 10 here, then you could say that 5 by 1 to the power of 3 or something like that, multiplied by 2, 5, let me see. You take out the 5 on the outside, 1 to the power of 3, and then you have 2 on the inside to the power of 2. You can't do that either. 5 by 1 is 5, 5 by, no. Right? These are things that you will flesh out in the course of your practice, which I am strongly recommending. I will provide my own questions as well, but wherever you could find the questions, get them and practice. I just wanted to get the basic understanding here. What you can do is, if you have a situation where, let me say, this is 25 to the power of, that was at 2? Yeah, to the power of 2. Because 25 itself is a power of 5, then that allows you to break it down and invoke some other laws which we come into in a little bit. So in this case, we could say that 5 cubed is 5 cubed, and then 25 is 5 squared in brackets. And then you're there. And then now that the bases are the same, you could proceed. And you'll have 5 cubed multiplied by 5. 5 to the power of 4. We'll come to that in another rule not too long from now. 3 plus 4 is 7. Nice? So the only way you could break down anything here is if you have a base, and if the other number that you're dealing with, or the other numbers that you're dealing with, can be expressed as powers of that particular base. So as a very quick example, without trying to work it out, you might get a question that looks like this. You might get a question that says simplify. You might have 125 to the power of 14 divided by 25 divided by 25 to the power of 9 or something like that. And they tell us simplify. 125 is a power of 5, 25 is a power of 5, bap, 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 boom, question done. We leave that for another time. Probably we'll work it out when we get to one of the other rules. Nice? So the bottom line, after all the talk at the end, is that anytime you're multiplying two bases that are the same, remember that is the bases must be the same. Then you add the power and you have the same base on the outside. So a to the power of m multiplied by a to the power of n is a to the power of m plus n. Not to be confused with our regular multiplication, where we would have, for example, ma plus na is equal to, let me say, m plus 1. No, let me write it. Let me follow the same pattern here. If we have am, as in a by m, plus an as in a by n, we can write that as a multiplied by m plus n. This is not the same as this, as you could see. This is multiplication here, multiplication here. You have a common factor which you could take out using factorization, and you have m plus n as the product inside here. This is a a, not a 9. That is multiplication. With exponentiation now, you have a common base. Big difference. You have a common base. And instead of, I forget the word I just used here. So you have a common base here, and then you have the m plus n as the other factor, as not as the other factor, sorry, as the power on top. So look at these two. Let me clear the rest of the board, right? Because it is important to understand the difference between multiplication, which is what we did dealing with here. Multiplication, multiplication. You add the two of them, and then you take the common factor out, and you have the product inside here. Product is 0. Right? You have the remaining product inside. Whereas up here, you have exponentiation, common base, common base, common base. So in other words, the A is common to both of these here. You take it out by factorization, and you have the product here. The A is common here, but in a different way, in a different form. Here, it is a common factor. Here, it is a common base. And with the common base, you have a totally different set of rules. Because here we multiply, we're not adding here. And then A here is your base, and your power would be the sum of the powers here. What you do not want to do under any circumstance is this, where you have A to the power of m plus A to the power of n. You cannot apply that rule if you're adding the two bases. You can't do that at all. At all, at all, at all, at all, at all. In that case, what will happen is that we will get another version of this depending on which one is bigger or smaller. We'll know what to do. So for example, if I have, let us say we have, let me say we have 5 squared plus 5 to the power of 3. Right? In that case, I could factorize and say 5 squared as a common factor into 1 plus 5. And we move on with that. Right? So even if you have two common bases and you're adding, in that case, what you'll have is a version of this, not this. This rule is only and only to be used when you're multiplying the common bases, not when you're adding. If you're adding the common bases, then you will have to invoke your regular factorization. And then you simplify accordingly. You'll have to, depending on which one is smaller, then you take out the common factor and you proceed, etc., etc. So we have to be very, very, very careful when we're dealing with multiplication versus exponentiation. And this is one of the reasons why I'm talking so much, because there is so much things in there that a lot of teachers and a lot of textbooks wouldn't really spend the time to explain, because it would mean spending the time to explain it. And sometimes people might shy away from spending the time to explain it. That, however, is not my modus operandi. I will put it on the table. I will encourage you to take it. Whether you take it or not is up to you. But it is there. There is a lot of small details in these things that we cannot take for granted. Nice. So A by m, A to the m by A to the n is A to the power of m plus n. So let me do one more rule and we'll close off this particular video with that, and then we'll go on to some of the other rules. So following closely on the heels of this one is the other version, where instead of multiplying the common bases, we now divide it. So instead of the multiplication sign in there, we now divide it. And as we would expect, if something happened here on the left side, then it is almost certain that something will happen here as well. And yes, indeed, something does happen. And what is that something? That something, as some of you all would probably have guessed by now, is that the addition sign will now change to a subtraction. So in other words, The third rule of indices is that a to the power of m divided by a to the power of n will be a to the power of m minus n. And again, just as we did, we could illustrate using some examples. We gotta get any duster here, boy. Papa, you. Pressure. Yes? So we're going. So if we say 11 to the power of 3 divided by 11 to the power of 2, that is 11 to the power of 3 minus 2, that is 11 to the power of 1. If I say 15 to the power of 9 divided by 15 to the power of 14, then that is 15 to the power of 9 minus 14, which is equal to 15 to the power of minus 5. So you see we have negative indices too. We will discuss what that means a little later on. Alright? If we have, let us say, let me put in a decimal just for the sake of argument now, make life a little more interesting. 2.5 to the power of 3 divided by 2.5 to the power of 6 divided by 2.5 to the power of 3. That is 2.5 to the power of 6 minus 3. That is 2.5 to the power of 3. Alright? Etc. We could work some fractions too, man. Let me bring some fractions into that. It happened with fractions too. So if we have 3 over 2 to the power of 4. No, not 4. Let me make it a 3 over 2 to the power of 7 divided by 3 over 2 to the power of 4. The answer to that is 3 over 2 to the power of 7 minus 4. And that is 3 over 2 to the power of 3. Etc. 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 And just as was the case where we had the multiplication, we could take a similar approach where we compare what happens with the multiplication and what happens with the division. So just as we did when we had the a by m to the a by m multiplied by a to the power of n, it's the same thing we're doing here, right? So let us say, again, I'm taking the time here now to explain the difference because it has certain mistakes that I don't want you guys making. So if you have, for example, we're doing the same thing like last time, am, let me say minus an. See where I'm going? That is equal to a multiplied by m minus n. Again, this is multiplication where instead of the plus sign in the middle, we have the minus. And similarly, if we have if we have a to the power of m minus a to the power of n, the answer is not a to the power of m minus n. That is not. So in other words, if people choose to do this anywhere, then you're almost certain that that is wrong. A to the, well, not almost certain, you're certain, you're sure. A to the power of m minus a to the power of n is not a to the power of m minus n. Do not confuse this with this. This rule here in black can be used only and only when the operation involved is division, not subtraction. So if the bases are the same as they should be, so in other words, two things have to happen if we have to contemplate this rule. The bases have to be equal, first of all. And secondly, the operation has to be division. So in this case, just as was the case with the multiplication, well, previous rule, right? Common factor, look at here, A. Let me make it look more like an A now, instead of making it look like a 9, right? The common factor is A, and then you have the product m minus n on the inside, right? No problem. And over here, you have the common base. Note the difference between the common base, which is what we do here when we have powers, and the common factor, which is what we have when we multiply. A multiplied by m, a to the power of m. Big difference. A multiplied by n, a to the power of n. Big difference. And in the same way, a multiplied by m minus n is different to a to the power of m minus n. So once we talk in powers, same base, operation is division, m minus n. A to the power of m minus n. Common factor, take it out, you're multiplying a by m minus n. And of course, just to reiterate, do not make this mistake where you see a to the m and you see a to the n with a minus sign in between them and then say, aha, a to the power of m minus n. No. That only happens when the operation is division, not subtraction. So with that, I will end this video. So we would have covered 3 rules of indices, powers, exponents, whichever vocabulary you choose to use. Stay tuned, we have a few more coming up. And later on, you'll start to get a sense of how they tie into each other. Because you'll realize eventually that one rule is just a slightly different expression of the same rule. So for example, I can say now that rule 3 is just a different version of rule 2, right? With the division and the multiplication, etc., etc., etc. We'll do that later. So for now, that is it. First rule, a to the power of 0 is equal to 1. Second rule, a to the power of m multiplied by a to the power of n is a to the power of m plus n. And the third rule, a to the power of m divided by a to the power of n is a to the power of m minus n. End of discussion. Stay tuned. We have more coming.